Thank you, Jesus. It's a great pleasure to be in Baracos. I'm about to give this a picture, so that's a comment on that beautiful PhD yesterday. The question is to know where to find the twisted sounds of Banach spaces, and I have the answer to this question. You find them in Baracos. Definitely is the right place for such things. Okay, so this meeting, this gathering is devoted to CK spaces, but I will only be dealing with spaces that absolutely everybody in this room know very well. That is, which are both CK spaces, of course, that is capital and infinity, which will for me be the usual one, that is capital and infinity as a unit interval equipped with a Lebesgue measure, which is, of course, a CK space. And I will denote by C the space of continuous functions on the unit interval. Of course, these are familiar objects. This one is non-separable. This one is separable. And I will only gather a few remarks relating very usual operators with some result and rather problems which are relevant to descriptive set theory. So I will denote by integral just the anti-differentiation operator that goes from an infinity to C. And the notation denotes exactly what you guessed. That is, if I apply it to a function f, the value of the integral at x is integral from 0 to x of f of t dt. So this is only the anti-differentiation operator. I take this chance to say that if you are interested into anti-differentiation, I just received this morning a beautiful book by Gonzalo Martínez-Cervantes, who's here. So all that you wanted to know about anti-differentiation and never dare to ask will be in this book. Okay, now I need some notation which is not completely classical. The range of this operator, which I will denote by lib 0, is exactly the space of all Lipschitz functions from 0, 1 to R, which vanish at 0. And the classical Lebesgue differentiation theorem tells you that any Lipschitz function is differentiable almost everywhere and is actually the antiderivative of its derivative. Okay, so this is fully classical. And one notation which is slightly less is what I will denote by dB. This is the set of all functions f on 0, 1, which are the derivative of some Lipschitz function but I request this Lipschitz function to be everywhere differentiable. Okay, so dB denotes the functions which are at every point and not almost every point the derivative of a Lipschitz function. So dB is a closed subspace of an infinity. That's a very easy lemma from real analysis. And I need a notation for the set of all the range of the anti-differentiation operator. This is what I will denote dB0. That is all Lipschitz functions which vanish at 0 and which are differentiable everywhere. Okay. This is, of course, subspace of C, but it is, of course, dense for the uniform norm and not closed. Okay, so this again are very familiar object, and I will focus on the Borel structure here. You know, L infinity equipped with the norm is a non-separable space, of course. But for the weak star topology associated with the trivial capital N1, then it becomes a contiguous union of a trisomal compact set. So it's a very much better topological space. And let me state a proposition which fits well into what I want to do. The anti-differentiation operator from L infinity to C is weak star tau p continuous and a Borel isomorphism between L infinity equipped with a weak star topology and a lib 0 equipped with a uniform norm. Okay, so this proposition is practically trivial. I mean, tau p, what I denote by tau p is a pointwise convergence on 0, 1. Okay, and why is it weak star to tau p continuous? Simply, I would say by the very definition, the integral of f taken at some point x is the integral from 0 to x of f of t dt, which is simply the duality bracket between f and the characteristic function of 0x. And so this trivial equation immediately shows that we have weak star to tau p continuity. Okay? And the Borel isomorphism with lib 0 with the norm topology is simply because if you take the unit ball of lib 0 with the norm topology, this is homeomorphic to the unit ball of lib 0 equipped with the pointwise topology. This is just by equicontinuity of the so-called Ascoli's lemma. Okay, and by compactness, this anti-differentiation is weak star to norm infinity an homeomorphism because it's continuous and one-to-one. And since you can replace in the ball norm by tau p, it's an homeomorphism from weak star to tau p in the ball, and then if you take the union of these balls, what you get is a Borel isomorphism. So that's one way to think of an infinity with a weak star topology, since lib 0 was a uniform norm. Okay. I should say, and that's an easy exercise, that we have a Borel isomorphism between these two things, but it is discontinuous in those directions. That is, anti-differentiation gives you the same Borel structure, but it is not continuous from weak star to the infinity norm, and the inverse operator, which is of course differentiation, is also discontinuous from the infinity norm to weak star. It's an exercise. A good exercise, actually, if you have a graduate course, you can use most of what I say for tormenting the students. Okay? Well, okay, so all this is very simple. Now I will use, I think I will erase this, or maybe even dare. I will dare something very risky, which is turn this whiteboard on the other side. That's the top of the technology I'm able to handle it. I did it. And there was no surprise on the other side. It was already clean. Okay. Now I will recall things which may be less familiar to some people in this room, which are analytic and co-analytic sets. So these are objects which were born after the French Revolution done by Borel, Lebesgue, and Baer, when the Russians realized that Lebesgue had been wrong by saying that the continuous image of the Borel set was Borel. So let me explain what this is about. Analytic is also a bad word in a sense because it is used for many things. So if P is a Polish space that is complete, metrizable, and separable, and Q is another Polish space, a subset A of Q is said to be analytic if there exists a F from some Polish space P to Q continuous, such that A is actually the range of F. Okay? And actually, it's an easy exercise to see that it's if and only if there exists F from omega to the omega or n to the n, if you will, the bare space to Q continuous, such that F of n to the n is equal to K. Okay, so that's, if you wish, a definition, which is due to Suslin a little more than a century ago. And if B contained into Q is Borel, then B is analytic. But the converse is wrong. And actually, Suslin's separation theorem says that B is Borel if and only if B and its complement are both analytic. The complicated direction being, of course, that if they are both analytic, they are both Borel. Okay, so this is the so-called separation theorem. More deeply, Suslin showed that if you have two disjoint analytic sets, they can be separated by a Borel set. So when it's a complement, there is no possible separation except the set itself. Okay. So this is to say, by the way, that if you take a Borel subset of a Polish space, you can refine its topology to make it complete. So a Borel set is a complete set which doesn't really know it is complete, but this is a very powerful trick if you wish to construct Cantor subsets, or all what completeness gives you still works for Borel sets in general. Okay, and as a consequence of the separation theorem, there is this Suslin losing a Borel range theorem, which says the following: if F from a Polish space to another is continuous and one-to-one, then F of P is actually Borel. The one-to-one image of a Polish space is a Borel subset of the range, and this is a deep and useful result. Okay, now, if A is analytic, then the usual notation says that its complement Q minus A, let me call it C, is of course co-analytic. The word has been pronounced by Antonio yesterday during the discussion after the Gilles presentation, and this is a beautiful collection of sets. So it's a word in itself, but I should say that in the co-analytic world, what plays the main role is omega 1, the first uncountable ordinal. I mean, it was presented yesterday. I don't need to define it again. So on the analytic side, it's rather C. On the coanalytic side, it's rather omega 1. And these two things are, in a sense, different. I mean, it's a large subject. So if C is coanalytic, then C can be written in a natural way as an uncountable union of Borel sets. And this is somewhat canonical. I cannot say really more, but there is a natural map, and I will see an example immediately. There is a natural map from C to omega 1, which we call a coanalytic rank, and B alpha is a set of all x in C, so that delta of x is less or equal than alpha. Okay, so this map is semi-canonical. I mean, there is no uniqueness in the coanalytic rank you can define in a coanalytic set, but it's somewhat unique, somewhat canonical. I would not say that. Antonio is a very good reference for this if you want more pertinent information in this. Okay. Of course, when C is not Borel, this union is non-trivial, meaning that you actually need all the countable ordinals. You don't need all of them exactly when C is Borel. It's a quantitative way to express the Slin separation theorem. Quantitative and useful way. I mean, in balance space theories, this has been used a lot in the last 20 to 30 years. Okay, now I will put together this theory with the anti-differentiation operator, and then my starting point will be another old result of Mazurkiewicz, one among the very important contributions of the Polish school in the 20s and 30s. So Mazurkiewicz showed the following in 1936. If you consider the space of all what I call DBs, this is contained into C, that is all functions F, so that F is Lipschitz, differentiable everywhere. This is what I call DB before. This space DB is coanalytic non-Borel in the usual space C of continuous functions. Okay, that's a beautiful result. And by the way, if you meet a student or sometimes even a colleague who tells you all the sets you will meet in your life, all the sets you will meet in the streets are Borel, no, this is not true. I mean, that's a set which definitively exists and which is not Borel. If this colleague tells you all the sets are measurable, then okay, you can shake his hand and tell him he's right. But if he tells you they're all Borel, then you must hit him on the head with this Mazurkiewicz result. And by the way, why is it so important? That's because this DB is the union of Aleph 1, of exactly omega 1, I mean, Borel sets, and the fact that you need all the countable ordinals explains, and this is actually a theorem, I mean, that in every method which allows you to anti-differentiate every bounded derivative, such as bourgeois totalization, for instance, you actually need all the countable ordinals. Because it's really a way where you meet the limits of what you can actually compute. Okay, if you want to integrate every bounded derivative, or countable ordinals would be needed. which means in particular that it's absolutely impossible to reduce it to an algorithm. That's fact of life. You cannot denote all the table orders. This is the limits of what you can do. Okay, so now how can we apply this Mazurkiewicz result? So there is a natural rank on DB. Maybe I will briefly try, well, okay, I may try to define it. So what is a natural coanalytic rank on the space DB? Then you will do as follows. If f is a function of 0, 1, and I equal AB some subinterval of 0, 1, then you will define delta f of I to be just the rate of change of f in the interval I. This is obvious. And now, if f is any closed subset of 0, 1, you define df of f and epsilon. Epsilon is, of course, a strictly positive number. This is a set of all x in f, so that for any open set U containing x, there exist I and j intervals containing to U, such that I intersected with j intersected with f is not empty, and the absolute value of delta f of I minus delta f of j is greater or equals than epsilon. So this set is a closed subspace of f, and it is easy to check that if f is differentiable everywhere, and say with bounded derivative, then df of f epsilon is nowhere dense in f. So this derivative is actually in a paper by Dougherty and Kekris. Is nowhere dense in f. So what you do is the following. You start from f equals 0, 1. You consider df of f, and then you iterate it transfinitely, and then there is some ordinal. There is some alpha of epsilon less than omega 1, such that the derivative of order alpha of epsilon of 0, 1 is actually the empty set. And now you define delta f to be the supremum over epsilon positive of all this alpha of epsilon. And this delta f is less than omega 1 exactly when f is differentiable. And this is how you associate to f one ordinal which tells you how simple the derivative is. Okay? And this is a coanalytic rank in the sense I mentioned without defining it. So that's a natural rank. Okay. Incidentally, of course, you need, it's not difficult, but it's a little lengthy to explain it. You need Baire category theorem to imply this, to show this implication here. And actually, you know what Baire category, Baire theorems are my favorite thing on earth, essentially. I fed my family with it. It's grateful to these techniques. And Baire allows you, and this is one thing to keep in mind if you wish to apply it. Baire allows you to handle contable business really well. That is, what it permits you to do is, if you have one set, to cut it into pieces in a contable way. This is what you do in the differentiation process. And you need some contable ordinal which tells you how fast you were able to do. And so this contable ordinal is a very precious thing. And on the other hand, it's also allowing you of gluing together contably many things. So an elementary way to do that is to use series. of course. This is the first thing you need in analysis. But each time you have a series and you use a series for something, just sit down for a minute and say, can I do it with back category theorem? And 9 times out of 10, back category theorem will give you the same. But first of all, it gives you more than one example to show you they are plentiful. And second, you can publish an article with it, which is sometimes good if you want to request the community. So, but again, contability and there are just close relatives. You know, in what Alberto explained yesterday, there, in mathematical logic, their axioms are pushing towards the table all cardinals which are below C. You know? Martin's axiom is typically doing that. Something which is less than C is nearly omega 0, except that it is not omega 0. But you can extend with it many results which are true in the complete case. So it's again in that spirit of their techniques. And they are actually called their axioms very often. Baer himself would not have understood them, but they are still called their axioms. Yes. Yes, but okay. No. You're right. No, I mean, I think I wrote it correctly, but maybe I did not say it correctly. That is, there, alpha epsilon is the smallest ordinal for which you reach the empty set. But then you take indeed the supremum over epsilon of all these alpha epsilons. When epsilon gets smaller, alpha epsilon gets bigger. But I wrote soup. Okay. Okay, so maybe my soup is so bad that it tastes like a dip. Okay, it's definitely it's true that from where you are sitting, that's the supreme. But maybe I say it. Sorry about that. And thank you for. Okay, so now time is running fast. So now that we have this WorCKshop result and this differentiability index, then what one can do is the following. Just to give, this statement is essentially for showing more examples that could be of interest to someone. So let me call this a theorem, although this is very simple. So if alpha is some contable ordinal, let me call the alpha the set of differentiable functions which vanish at 0, so that the rank is less or equal than alpha. And it is not difficult to check that this is a vector subspace of C. And I will also note scrape the alpha, which is a set of all its differential, which is then a subspace of an infinity, and it is easily checked that this thing is closed in the uniform norm. Okay, the vector subspace is not closed. We will see in a moment what it is. The alpha, is closed in the Lipschitz norm, but not in the uniform norm. Okay, so now let me call this a theorem, although again it's a corollary of known properties of coanalytic frames. For all alpha less than omega 1, the alpha is uniformly closed subspace, vector subspace, which is Wickstar-Borel. And for all beta less than omega 1, there exists alpha less than omega 1 such that the Borel rank the Weak-Star-Borel rank of the alpha is more than beta. So Borel rank is not bounded. I mean, you have subspaces of arbitrarily high Weak-Star-Borel rank. This is due to the fact that if you have a coanalytic complete set, and if you write it as a union of its constituents, so the alpha, as I said before, the complexity of the constituents is unbounded. It's not a trivial fact, but it's a well-known result about ranks and, for instance, about the rank delta. The fact that it's a vector subspace is due to the fact that delta of f plus g is less or equal than the supremum of delta f and delta g. It's not obvious, I mean, but it can be checked in this way. And now, if you go on the other side, the integral of the alpha, which I call the alpha 0, is Borel in the infinity norm in C, and again of unbounded Borel rank in the previous meaning of it. That is, it can be of arbitrarily high Borel rank. Actually, one good question maybe for someone who would start a PhD related with descriptive set theory would be to have an estimate of the complexity. Here I'm just using the big theorems, but without getting down into the proofs or estimating the value of the Borel rank of the alpha. I'm practically sure that by sweating a little bit on this, you have an explicit estimate, more or less explicit. And this could be a good first question. I mean, I don't think there is a trap in which a student could fall. I mean, that could be a good training ground and not a trivial thing. Okay, on the other hand, if X contained into dB is separable, is non-separable, then the range of the map is Borel of small range, that is, it's K sigma delta in C. So why do I say that? I mean, I would like to be more explicit, but I have to be short. One of my goals when I wanted to apply Mazurkiewicz theorem was to find a better proof of a very nice result of Saint-Rémy. Saint-Rémy showed that if you have a separable Banach space and a linear continuous operator into another Banach space, by the Borel range theorem, the range is Borel. This is clear. But what Saint-Rémy showed is that it can be Borel of arbitrarily high class, which is non-trivial. It can be a Borel set of rank more than any alpha contable ordinal which is given. And I thought that maybe Mazurkiewicz theorem was providing a better proof of this. What the theorem says is that the answer to this initial question is negative. That is, you have those spaces, the alpha, whose range is of arbitrarily high Borel rank, but they are bound to be non-separable. If you start from a separable thing, the anti-differentiation operator gives you a stupid K sigma delta space. And it would be nice to have Saint-Rémy's operators built up for that purpose, but they are not natural operators. It would be nice to have natural operators from mainstream analysis which have this property. And what the theorem says is that anti-differentiation fails to deliver this type of result. So some new ideas. Mazurkiewicz theorem is great, but those operators with a complicated range have non-separable domains. That's a fact of life. Okay, now my time is nearly over, and I still did not mention too much of the Weak-Star-Borel subspaces of an infinity, except that all those d alphas are indeed Weak-Star-Borel of arbitrarily high class inside an infinity. But I would like besides those simul type operators, I would like to provide an open question, or a question which I believe is open. If someone has an answer, I would welcome it. I asked Antonio yesterday morning in front of a coffee. He did not know at the time. Maybe you know now. So the question is probably open. And so it's about weak star Borel subspaces of an infinity or little an infinity. Okay, incidentally, I will ask two questions which look like one, but they are actually two different questions. We all know that an infinity is linearly isomorphic to little an infinity. It's an easy application of Belchinski's accordion lemma. But any such isomorphism is not weak star to weak star Baire measurable. This follows from a nice result by Christensen. So an infinity with weak star topology is very different from a little an infinity with weak star topology. And so they are isomorphic only for the norm topologies, but the natural topologies, which are the weak star ones, I mean the handleable topologies, are very different. So my question is the following. Take X into an infinity, a non-closed subspace. Assume it is isomorphic to an infinity and weak star Borel, or weak star measurable in some way, but let me simply say weak star Borel. Does it follow that X is actually weak star closed? And question prime, same with little and infinity instead of capital and infinity. As I said before, these are two different questions. Okay, I don't know. And it would be, if you like, one example of a Baire dichotomy. Baire theorem is also useful for telling you that things are very simple or very complicated. There is no possibility between. Typically, if you have a linear form defined on the Banach space, it's continuous or it fails to be Baire measurable. It fails to be Borel or anything. It cannot be in between, very good or extremely bad. And it would be in the same spirit, okay? You take a copy of capital and infinity, which is reasonable enough, then it would be extremely simple, that is, weak star closed. Or if you want to state it differently, a copy of an infinity would be weak star closed or would fail to be weak star Borel. That is, you would need the axiom of choice to define it or anything. So I don't know. I would like to know. Let me just mention two special cases. If L infinity is a direct sum of two spaces which are both weak star analytic, in particular weak star Borel, then they are both weak star closed. So if you make the assumption on both spaces in the decomposition, then you are fine. But there are weak star closed spaces whose complement is not weak star Borel. So it's not enough to solve the question, okay? I would like to replace and by or. That's another way to state the problem. And another special case where it works is that if you take a space X, now it's in little and infinity, a space X which is stuck between C0 and L infinity, which is weak star analytic, say weak star Borel, for instance, and of course different from L infinity itself, then X is not isomorphic to L infinity. Actually, it's not complemented in L infinity. So in that case, you know that the answer is yes. Okay, but this is, of course, an extra assumption you had. So there are some results about automorphisms of L infinity going back to Lindenstrauss, but they break the weak star structure, so they don't seem to be usable. But this, at least, I can do. And my hope, and I will finish on this, I should actually finish now. My hope was that the d-alphas before could be useful for this. Because they form a very nice collection of weak star Borel sets, which are not weak star closed. But I was also disappointed to say that for all alpha less than omega 1, the spaces the alpha are not isomorphic to L infinity. I spent some time pondering about the question until I realized that differentiation was showing that they fear the Grothendieck property. That there's a sequence of integration of n times between E0 and E0 plus 1 over n is a weak star conversion sequence of an alpha, which is not weakly convergent. Therefore, Grothendieck property fails, and therefore they are not isomorphic to an infinity. So those good old the alphas are not providing the answer to this question. So if you want to make me happy, please solve it. And I mean, I love the question because, you know, those spaces are obvious. I mean, there are subspaces of capital that you can meet in real life and apply that, and it would be nice to know if they are basis. Sorry for having been too long. Thank you very much.
Very much. Well, it's a pleasure to spend this week here. So I would like to thank everyone who organized this, and specifically Alberto and Nazareth. It's always a pleasure to be in Badajoz. Okay, so, well, as we all know, if you look, for example, as closed ideals in the operators of the algebra operators on the Hilbert space, compact operators form the only closed two-sided, non-trivial two-sided ideal there. But once we go to other Banach spaces, and it's actually also true for the sequence spaces CU and LP, but once we go to other spaces, then other closed ideals appear. And so I will start with definition of pitch, which allows me to consider ideals in all Banach spaces at the same time. So operator ideals, in the sense of pitch, say I, it's actually the same as an assignment for any, for all pairs of Banach spaces so of a subspace of the space of linear operators from X to Y, requiring that this is not trivial, and it has to satisfy the ideal properties. So it's just the fact that whenever T belongs to I, so now we just write I, we don't need to specify where T acts, then UTV will still belong to I whenever U and V are operators such that this makes sense. So of course, if say T goes from X to Y, then V has to take values in X and U starts from Y. So this, of course, if you look just as I of X, then I of X will be an ideal in L of X, but you are adding also to define what it is to be in the ideal from between two different spaces. So important examples. Compact operator, well, actually, you could start with the closure of the closure of finite rank operators. Compact. I will mention here strictly singular operators. We won't really need them, so I won't define them. And I will add something here in essential. So let me comment here that by the works of Cato, we know that strictly singular operators are perturbation operators with respect to Fredholm theory. So if you add a strictly singular operator to a Fredholm operator, the sum is again a Fredholm operator. And this is actually this inclusion here. Then define an ideal by exactly those operators which preserve the Fredholm class, and this is actually strictly bigger than strictly singular operators. So that's so I will give the general definition, but let's just think that in essential means preserves Fredholm operators. So the only thing that will be relevant for us is that if you start with an isomorphism on the Banach space and add an inessential operator, then the sum will maybe not be an isomorphism, but at least a Fredholm operator, which means induce an isomorphism between finite codimensional subspaces. So preserves isomorphism up to finite dimensional parts, if you wish. And okay, I will not want to spend too much time on this part, but all these inclusions are strict. And of course, this one is the most difficult. This one is just a consequence and flow result about the application property of the others. We can find reasonable examples. Okay. So these are mainly the operator ideals we can work with. And so Peach defined an operator ideal to be proper if and only if I of X is a proper subspace of L of X for all X. Of dimension of infinite dimension. Well, certainly, if X is finite dimensional, and since we are putting a definition that it should not be 0, then automatically you have at least all finite rank operators, and in this case, well, I of X is equal to L of X. X is finite dimension. So we are only interested. I mean, things become non-trivial, of course, only if X is infinite dimension. A reformulation of this is what is defined as space of I should be equal to a class of finite dimensional spaces where space of I is defined as follows. So it is a class of Banach spaces, and X belongs to space of I if and only if the identity on X belongs to the ideal. Okay, so if the identity belongs to I of x, and I of x is the whole of L of x, and conversely, so those two are equivalent. Okay, well, of course, compact operators form a proper ideal. I mean, the identity of x will not be compact unless x is finite dimensional, but it's actually not difficult to prove it for the ideal of inessential operators. And since you see also that it is a hereditary property, so if I is proper, any sub-ideal of I is again proper. So if you prove it for an essential, you get it for all of them. And so what is the question of pitch about proper ideals? Oops. So question, he asks, is there is a largest proper ideal, let us call it U, that let us think something like a universal object, then this would mean if this were true, and because being proper is hereditary, it may mean that you could test if an ideal is proper by checking if it is contained in this universal, hypothetical universal object, right? That's probably the idea. There was a candidate which is the class of introjective operators, but it turned out that it's not an ideal. So, and this was a work by Ayena and Gonzalez, and I'm going to use a lot of their ideas in what I'm going to say here. Okay, so well, the answer is big no. In two ways. Yes, sorry. So the other question was, I mean, he asked if he conjectured that maybe the ideal of inessential operators would be such an example. So is such, can you prove it for you? So the answer is no. To both, of course. I mean, this one, one answer, a negative answer to one implies negative answer to the other, but we actually have a bit more details here. So in two senses. So first of all, you can construct a proper ideal which is strictly bigger than the ideal of inessential operators. So, well, certainly this will not be the largest proper ideal, but it's not even maximum. And two, and using the construction of one can actually obtain. So yeah. So let me say here. So first of all, you construct such an object. I will explain how you do it. And then what you can do is you can, because the construction depends on some parameters, so you can construct two versions of V, which I could call V1 and V2. Such that the sum of the two is not proper. So immediately you see that there cannot be a largest proper ideal. If there was, if you have an ideal which contains all proper ideals, it has to contain V1 and V2. Since it is an ideal, it has to contain the sum. The sum is not proper, and since proper is hereditary, this object cannot be proper. And I should thank Antonio for Martínez-Cervantes for pointing out that in the previous version of my work that actually the result could be formulated in this way, in particular the one. Okay, so maybe I will go back to the other side because I want to give the formula for this object. Okay, so, or maybe not, maybe I will put it below here. I just want to keep it, but let us for now stay on this side. So here I want to give the formula for this V. So V will be the sum of the ideal of inessential operators plus something. Something will be things here that I will define. It's more pleasant to have something which is closed, so I'm taking the closure here. And I should already point out that it's not a very natural ideal, right? It will not be as nice as natural as the previous ones. So what are the objects considered here? So first of all, X of S is a certain space of Gaussian-Murray, shift space. It's not the original HI space of Gaussian-Murray. It has to be, it's something with different properties, but still an exotic space. And two, Y is a certain infinite, well, infinite dimensional, of course, but actually the point here is that it is infinite codimensional subspace of XS. Well, when we construct the two different versions of V, we just make two different choices for this subspace here. And so I should maybe here mention that this such a Y was considered initially by Ayena and Gonzalez in 2000, and this Gaussian-Murray is from 97. So maybe here I can put the definition of these things. So first of all, what you can define is op of X for Banach space. So T belongs to op of X if it factorizes through X. So you can write T as UV, say, so T V U. So T could be, I don't know, from Y to Z, I mean, W to Z, arbitrary spaces, and you want to factor through it. And so this was considered by Teach. I mean, it's a classical notion. And what do I mean by this? I mean, the union over N of op of X to the power N. So factorizes through some power of x. So let me talk a bit about 3. This is something new with respect to what Ayala and Gonzalez were doing. They were more or less implicitly considering op of x, and one of the new ingredients is here. So let me comment on it. So I'm going to erase maybe a question here. Maybe it's good to have the definition here. I'm going to use this bar. So the whole point here is that if you consider 2 operators which factor through x, so maybe, yeah, so two decomposition witnessing that T belongs to factors through x. And if you want to look at the sum of the 2, then you will write things as u prime times v prime. And so you will see that it naturally factors through x squared, not necessarily x, especially if x, of course, unless x is isomorphic to square, for example. So, so it means that op of x is not necessarily in general an ideal. But if you allow factorizing through powers of x, then you will get an ideal. The question of composition on the left or right is not a problem. The problem is really with the sum, because of course now, well, you can see, of course, here if I had assumed that it was in op of xn and of xp, then here it will factor through n plus p, and so I have solved this question of having an ideal. So the point of using this is to guarantee that this is an ideal, and so VI is an ideal. Okay. Okay, what's next? Next thing is on the next slide. Additional properties of VI. So so one very important feature here is that you can construct an operator Ti for e equals 1 and 2 from x to yi, such that the sum of the two, so T1 plus T2, is essentially the identity on XS plus a strictly singular part which doesn't matter here. And that's part of Ayala Gonzalez paper. And as a consequence, well, there are two consequences for this. A, well, you see that the identity here is a Fredholm operator on XS, and well, you can see Ti as an operator on XS as well, and T1 is not, because Yi is infinite codimensional in XS, and so T1 is a T2 perturbation of a Fredholm operator, but it's not Fredholm, so T2 is not. T2 does not preserve the Fredholm class, and so T2 is essential. And same for T1 also. So Ti is essential. That was the point of Aina Gonzalez's work, to try to find an operator which is inessential, but with some other properties that we don't need to think about now. And B, well, since you can obviously see that Ti belongs to Vi, because Ti goes from Xs to Yi, so it factorizes through Xs and through Yi in a very obvious way. So if you take the sum of the two, which is the identity of Xs, that's something which doesn't matter, belongs to the sum of the two ideals. And so this ideal is not proper because I found the identity of some infinite dimensional space belonging to it. So what did I get through all this? I got an ideal which is strictly bigger than the ideal of inessential operators, because Ti is in it and is not an essential. I have this condition that guarantees that the sum of the two is not proper. And the last thing to do is to prove that Vi is actually proper. So, yeah. So let me see how much time I have. So I maybe take 5 minutes to conclude here, and then 10 minutes to talk about possible extensions. So, okay, so I want to keep the formula here. So generally is here, and remember, so if we all agree, the last thing to show is that Vi is proper. Okay. So then we have to use the exotic properties of Gauss and Morris space. So the point here is that this is a space which has very few projections, which I'll see in a minute how we use that. But let me use the opportunity to point out that even though it will have few projections, it needs to have sufficiently many operators, because we wanted to be able to construct these operators T1 and T2. And so, for example, just a HI space would not work because the HI space has very few operators. Since every operator is lambda identity plus strictly singular, you don't have inessential operators apart from Freldom operators, and so the thing does not work. So it really has to be a space with few projections, but still some operators. So yeah, so why is Vi proper? So the point is that you're gonna so you have a theorem. I mean, a way of describing the properties of Gauss-Morel is as follows. They prove that no complemented subspace of Xs is isomorphic to a complemented subspace of Yi. Actually, this would hold for any infinite codimensional subspace of Xs. And this comes from the fact that the only complemented subspaces of excess are the finite codimensional subspaces, but okay, we don't need to go into more details here. And so what I had to add to the scenario here is that this actually extends to any power of xs, and here any power of the infinite codimensional subspace. Luckily, there was no need to construct a new space to have this, and most of the techniques were already there. It was a bit of work, but no really new ingredient was needed. So this is what we need. Of course, this corresponds to having to use op less than omega instead of just op here. So it's a multi-dimensional version of the results, and let us see why what happens from this. So consequence, assume that the identity on some space Z belongs to Di. Oh yes, so I forgot to say as a comment, it's easy to show that it is enough to prove that this is proper, because it's not difficult to show that if this is proper and you add the ideal of initial operators, it's still proper, and also it's not difficult to show that the closure of the proper ideal is again proper. So it boils down to proving that this is proper. So what I mean to take as a hypothesis here, if the identity belongs to this intersection, so let's say directly up of xsn and also up of yp for some n and p. But it's really easy to see. So if the identity of z factorizes through xsn, then it's very easy to see that then z embeds complementarily in xsn and in yp. I mean, this is equivalent. Well, and then by the theorem, well, here, okay, I meant infinite dimensional, of course. I implicitly use the convention subspace. By subspace, I mean infinite dimensional. Well, because of this, then dimension of z has to be finite. And this is exactly telling you that, that this is proper, right? Okay, so questions? I forgot to say that this is a C of K space conference, and at this point I haven't talked about C of K. It will come at the end. Don't blink. So I want to conclude with discussing what could be, how those results could be extended. And I'm staying on the same side of the board because I want to keep this formula. So this question about proper ideals, it can be seen inside more general context. So on one side, you have the operator ideals of Peach. And you also have the notion of space ideals. Which are denoted by A, which is a class of Banach spaces. And well, you have a formal definition, certain condition on the class of spaces. Well, you want the finite dimensional spaces to belong to be included in it, just not to be trivial, and it has to be stable by taking direct sums. So xy belongs to A, the sum should as well. And by taking complemented subspaces as well, so if x belongs to A and y is complemented in x, then y belongs to A, which also tells you that it's stable by isomorphism. This means embeds complemented. And now remember that I defined. Sorry? Oh yeah, but that's included here because here I'm talking about complemented embedding. It's not subspace. It's just why embeds complemented. So one example is what I defined previously, the space of I. If I is an ideal, then the space of I will be a space ideal. Recall that X belongs to the space of I when the identity of X belongs to I. Conversely, if you start from a space ideal, it is actually always the space of an operator ideal. So what you can do is just consider op of A. You can guess that it means so an operator belongs to op of A if it's factorized through X of some X in the family A. And it's easy to show that A is always the space of op of A, which proves that any space ideal is the space of some operator ideal. So after you have this correspondence, you can think, of course, of so finite rank operators will correspond to finite dimensional spaces with this correspondence. Okay, so now if you take one question, the more general question by Peach is given A, of course, a space ideal. Well, you can always write it as the space of some ideal E, some operator ideal E. Is there a maximal, a largest I with this property? Does there exist the largest I such that the space of I is A? Of course, we know, well, we just proved that the answer is no if A is a space ideal of finite dimensional spaces. Okay, so the point is that we can actually give a partial answer in some cases. So I will say, maybe I have space here to do that. No, if all spaces no if for all X in A, X is totally incomparable with XS, a Gauss-Morey-Schiff space. So example, if you take A to be the family of
Hilbertian space, well, I mean isomorphic to a Hilbert space, well, Gauss-Morel space does not contain a copy of L2, so or any Hilbertian space, so there will also not be a largest ideal amongst those for which the space ideal is precisely the space ideal of Hilbertian space. And so this is not a too difficult adaptation of this technique. What you do is here you take, you change this up, adding up omega A, and so the definition is that an operator T belongs to this or to some, well, for an arbitrary X if T factorizes through the direct sum of A and Xn or some space A in A and some N in N. And so this guarantees you that this will imply that the space ideal of this will at least contain all elements of A, but no more than that because of properties of complemented subspaces of such direct sums, which of course total incomparability tells you how to describe well the complemented subspace of such a sum, and so it boils down to the previous situation. Okay, so but my point to conclude is as follows. That this question here, it is still open for, as far as I know, for space ideal of reflexive spaces or for the space ideal of separable spaces. Of course, you cannot use this criteria here because XS is reflexive and separable. And so maybe if you want to solve this here, you need a non-reflexive version of XS, or for separable and a non-separable version of XS, but which should still be somewhat universal because one thing which works very well when you are working with proper ideals, so related to finite dimensional spaces, every finite dimensional space embeds in any infinite dimensional Banach space. And once you pass to this context, you probably need a space which contains a copy of all separable Banach spaces. It has to be separably universal. So anyhow, to conclude, maybe we need some non-separable version of Gauss-Morel space. Why not a C of K space? And that's the end of my talk.
So you are concentrating there, where you want all X and A to be true.
Yeah. So I just put here something which works, but certainly you can put something weaker here, and probably essentially comparable would work. I mean, according to what you are working with, you should put something a bit more precise here, certainly.
So, you mentioned. Oh, thank you. Okay, now I feel powerful now with this microphone. Valentin, you mentioned that the ideal that you denote by the I is not natural. I mean, and a little bit more precisely, this reminds me of things Tim Gowers wrote at the time when they created with Morel these strange spaces. Probably you need one way or another, a norm defined by some implicit formula, if you wish to write down your space excess or such things. So is there, could be an ambitious question, but is there any hope to show that if you restrict yourself to ideals for which the norms are easy to define in a way that should be, of course, explained precisely, that in that specific class of ideals, you may have a maximal proper ideal or something like this?
Yeah, that would be a very interesting direction. I didn't think of that, but yeah, trying to give a sense to natural ideals. That would be interesting. I just want to comment that here the point about this subspace Yi is that it should not be complemented in XS, and because the way it is defined it's constructive, but it's not very explicit. So the only way we guarantee that Yi is not complemented is by using the property that no infinite codimensional subspace is complemented. That's very strong. Mm-hmm. So maybe there could be possible to use a less exotic space if we discriminate a bit better the subspace here. But...
Okay, thank you, Valentín.
Thank you. Okay, so I'm going to talk about some results and questions concerning sequential properties in dual balls with the weak star topology. So let me start introducing what are the sequential properties that we are going to consider. First of all, you all know what is a sequentially compact space. We are going to deal also with Frechet unison properties. About a compact space is Frechet unison. If whenever you take a subset F and a point in the closure of F, then you can find a sequence in F converging to the point, and the compact space is sequentially closed. Well, it is sequentially if any sequentially closed subspace is closed, and by sequentially closed I mean a subset which is closed under taking limits of sequences. And finally, we are going to deal with countable tightness. So compact space has countable tightness if whenever we take a subset F and a point in the closure of F, we can find a countable subset of F having this point in its closure. So we are going to deal with these four properties. They are related in this way. And well, before going further on the discussion about these properties, let me introduce, let's say, a quantitative version of sequentiality. So suppose that we have a topological space and we have a subspace F of T. Then we can define the alpha sequential closure of F by induction on alpha. Alpha is just an ordinal. So first we take the set. Then S1 of F is the set of limits of convergent sequences in F. In general, for any successor ordinal, we just take the previous set and take the set of limits of sequences. And for limit ordinals, we just take the union of the previous sequential closures. So under this language, notice that the omega-1 sequential closure of any set is always sequentially closed. So if we take a sequence here, then the sequence belongs to some S alpha with alpha countable ordinal, so the limit belongs to S alpha plus 1, so this is always sequentially closed. So in other words, this means that to be sequentially is essentially the same, that the omega-1 sequential closure of any set is just the closure of the set. So we are going to say that the topological space T has sequential orders more or equal than alpha if the closure of any set coincides with the alpha sequential closure of the set. Okay, so now let me say a few things concerning these implications. On the one hand, whether being sequentially compact implies sequentiality, this is not true. In general, for example, we have the compact space consisting of the interval 0 omega 1, which is sequentially compact, any compact line is sequentially compact, but it does not have a countable tightness and therefore is not sequential. And whether we can distinguish between countable tightness and sequentiality is undecipherable in ZFC, so this is known as Moore-Rufka problem. And well, under the continuum hypothesis, there are examples of compact spaces which do have countable tightness, but which are not sequential. And under the proper forcing axiom, these two properties are equivalent. And the most natural example of a compact space which is sequential, but not per se unison, is essentially this compact space that you like a lot, the one defined by a maximal almost disjoint family. So let me recall a little bit the same notation that Alberto used yesterday. Recall that this is a compact space which is scattered of height 3. So we have a level consisting of isolated points, which we identified with n. Then we have a level consisting of points of the form PA, where A belongs to F, where F is a mad family in N. So this is a maximal, almost disjoint family. And then we consider the one-point compactification of this set. So in this compact space, which Alberto denoted by K sub F, where F is the mad family. So what do we have? We have that any sequence here has a subsequence converging to a point in this level, and any sequence in this level consisting of different points converges to the point of infinity. But this level is dense, and no sequence here converges to infinity. So in this compact space, we have that the second sequential closure of any set is the sequential closure of any set, but in particular, for the natural numbers, this is not the closure, okay? Because this point does not belong to the sequential closure. So this compact space here is the most natural example of a compact space which is sequential but not per se unison. And indeed, you may think that if maybe playing with mad families, we can define an scattered compact space of height 4, and in such a way that the sequential order is 3 and not 2. Well, it is unknown if such a thing can be done in ZFC. In the continuum hypothesis, this can be done, but in ZFC, we do not know if we can add levels in such a way that we have sequentiality with higher degree. So essentially, this is the only known example of a compact space which is sequential but not per se unison. Okay, so we are going to deal with this for properties, as I said, in the dual balls of Banach spaces. Whenever talking about, let's say, unison, we are going to say, instead of Weierstrass let's say unison dual ball, we are going to talk about having Weierstrass angelic dual. And we are going to also consider convex versions of these properties. So first of all, the convex version of having Weierstrass angelic dual, of having Weierstrass let's say unison dual ball, is what we are going to call property E of F remote. So a Banach space has this property if whenever we have a convex subset C in the dual ball and a point in the closure, we are able to find a limit converging, we can start converging to this point. So if I remove here the word convex in this definition, then what I get is that we can start with a unison dual ball. And well, we do the same with the concept of being sequential. This is essentially the same, but just for convex set. So this is the convex version of having Weierstrass sequential dual ball. And the convex version of having dual ball with countable tightness is what we call property C of Coulson. So a Banach space has property C of Coulson if and only if every point in the closure of any convex set belongs to the Weierstrass closure of a countable subset in this set. Indeed, property C of Coulson is originally defined in a different way, and this is known as false characterization of this property. And well, let me say that indeed Paul asked whether this condition here is in turn equivalent to have countable tightness, dual ball with countable tightness. So it is unknown whether one can distinguish between property C of Coulson and its non-convex version. So if we go again back to the previous diagram, then what we have are these four properties. So recall this is per se unison, this is sequential compactness, and this is countable tightness. So this is essentially the same diagram than before, but just for dual balls with the WorKshop topology. And now we are going to add the convex analogs of this version. So this is the convex version of the Z unison. This is the convex version of having WorKshop sequential dual ball, and this is the convex version of countable timeless. So we have these implications here. It is not difficult to check that we also have these implications here. And I haven't defined a convex version of sequential compactness of the dual ball. I'm not going to give the definition, but most of you already know. This is known as WorKshop convex block compact dual ball. So instead of saying that every sequence has a WorKshop converging subsequence, in this case, what we do have is that every sequence has a WorKshop convex block converging subsequence. We play with convex combinations of the sequence. And again, while making some computations, it can be checked that this implication also holds. So we have this diagram here. And again, as before, we may wonder whether the converse of these implications hold or not. So these two implications here are not, does not hold, do not hold. If the implication is written in red with this cross, this means that the implication does not hold. Okay? So a counterexample would be just the space of continuous functions over the interval 0 omega 1. The implication here does not hold, and this is just because having WorKshop convex block compact dual ball is a very general property, much less restricted than having WorKshop sequentially compact dual ball. So, for example, any Banach space not containing little L1 satisfies this property as WorKshop convex block compact dual ball. But there are Banach spaces which do not contain little L1 and not having sequentially compact dual ball. So this would provide a counterexample to this implication. And well, as we said before, these two properties are at least equivalent under PFA. So they are consistently equivalent. Okay. And also we have Paul's question, which asks whether these two properties here are equivalent or not. And this is totally unknown in set of C. Okay, so during the talk I'm going to focus on two questions. Well, on whether these converse implications do hold or not, and on whether these properties are free-space properties. Okay, so as Gilles said yesterday, I thought it's the word capital of Crystal Sam, so maybe this is the best place to post this question. So let me do this in following the spirit of Jesús Castillo and Manuel González. So like in his book, I'm going to write all the properties, and I'm going to do this like in the table of the final of the end of the book. So in the book you can find these two properties, sequential compactness of the dual ball, and also property C. So in the second row, they write whether the property is a three-space property or not, or whether this is open. Then in the third row, they write whether the ideas of the counterexample or the ideas of why this property is a three-space property, and a reference in the last row. So this is contained in the section 4A, and this is contained in the section 4A. Okay, so as far as I know, the rest of the properties are not considered in the book, so let's try to complete the table. So, well, in the case of sequential compactness, this is a very interesting sample. This is just a CK, which is a twisted sum of C0 and a CK space. So in such a way that this K is the compactification of the natural number in such a way that the remainder is sequentially compact, but the copy of n does not contain convergent subsequences. So this CK space does not have sequentially compact dual ball, but C0 and this space here do have. So, and well, the fact that property C is a three-space property, this was proved by Paul. Well, let's see what happens with the rest of the properties. The first one, whether having WorKshop angelic dual is a three-space property or not. Well, the answer is no. This is quite simple, and this is essentially we can take the CK space with K, the compact space included by a Malt family, or just with Johnson in the source space. So whenever we take a Malt family, the Banach space associated to it provides a Banach space which does not have Wittgenstein angelic dual. And well, in general, here, if we take the Johnson in the source space, C0 and little L2 of gamma, these are the spaces with Wittgenstein angelic dual. In general, weakly compactly generated Banach spaces, weakly Lindelof determined Banach spaces, they do have Wittgenstein angelic dual. They are well-behaved spaces. So let's move to the following property. What about Wittgenstein sequential dual bond? Well, I tried to prove that this is a free-space property, but I failed. But at least I was able to prove the following. So suppose that X is a twisted sum of Banach spaces with Wittgenstein sequential dual bond. If I assume that this twisted sum X has Wittgenstein sequentially compact dual bond, then I can guarantee that X has Wittgenstein sequential dual bond. But I need to assume that the twisted sum has Wittgenstein sequential compact dual bond. As I said before, having Wittgenstein sequential compact dual bond is not a free space property. So this seems to not to be a free property. And well, indeed, we can rewrite this using the quantitative version of sequentiality. So indeed, if Y has sequential order smaller or equal than gamma 1 and the quotient has smaller or equal than gamma 2, then the Banach space X, the twisted sum, has sequential order smaller or equal than gamma 1 plus gamma 2. And the idea is quite simple. So suppose that we want to prove this theorem. So what we have to do is to take a subset F in the dual bond, a point in the closure of F, and to check that this point belongs to the gamma 1 plus gamma 2 sequential closure. By linearity, we can just deal with the point 0. Okay, so we want to check that 0 belongs to this set. And what we do is to take for every finite set A and for every epsilon, positive epsilon, just the intersection of F with the basic neighborhood of 0 associated to this A and to this epsilon. So 0 belongs to the closure of this set, since it belongs to the closure of F, and therefore it belongs to the closure of the restriction of this set to Y. But here, since by our hypothesis, this Wittgenstein closure is just the gamma 1 sequential closure of the set, we have that 0 belongs to this set here, and notice that this equality is written in red. We can commute the operator with the gamma 1 sequential closure. This can be done if the domain, if the dual bond of X is sequentially compact. Okay, this is the only step of the proof where sequential compactness is used. And once we have this, well, what we have shown is that for every finite set A and for every positive epsilon, there is a point in this gamma 1 sequential closure for which the restriction to Y is 0. So we can just take now the set of points of this form and now move to the dual of the quotient. Since this set belongs to the orthogonal of Y and this set here is just Wittgenstein homomorphic to the dual bond of the quotient, now we use the fact that the quotient has Wittgenstein sequential order smaller or equal than gamma 2, and we conclude that 0 belongs to this set here, but G is already contained in the gamma 1 sequential closure of F, and this is essentially the gamma 1 plus gamma 2 sequential of F, which is what we wanted to prove. So there is just one step where sequential compactness is used, and I don't know if this can be removed, this hypothesis. I bet this can be removed. Maybe it's not so difficult. So this is the first question I'm going to pose to you. So this is all we can say, but for the moment, well, at least this is enough to have nice consequences. So for example, if K is a scattered compact space with finite height or with countable height, then the corresponding CK space has Wittgenstein sequential dual bond. So in particular, the CK space associated to a Malt family is always a Banach space with Wittgenstein sequential dual bond. And well, the idea is just because we can take the Cantor-Dixon derivatives of K and to define a tower, increasing tower of subspaces, X alpha, consisting of those functions f, which are null over the alpha Cantor benediction derivative of k, and then in these spaces what we do have is that each quotient of this form is isomorphic to this space here, so in particular it has Weierstrass angelic dual, and since we have this theorem here, and the dual ball of any CK space with K scattered is sequentially compact, we do have this property here, then we can apply this to each step, x alpha, x alpha plus 1, so each x alpha has Weierstrass sequential dual ball, and at the very end what we get is that the whole space, the CK space, has Weierstrass sequential dual. Okay, so we also have a convex version of these results. So in particular, the convex version of having sequential dual ball with sequential order smaller or equal than alpha is what we are going to call property E alpha. So we assume that these two sets are equal for any convex subset C of the dual ball. And okay, so with this notation, property E of Abramovich is just property 1, property E prime is just property E of omega 1, and the previous result also holds using this convex version. Now instead of sequential compactness of the dual ball, we only require the dual ball of X having Weierstrass convex compact dual ball, and if we know that Y has property E of gamma 1 and the question has property E of gamma 2, then X has property E of gamma 1 plus gamma 2. Okay, so as I said before, this is nice, but I have to say that I don't know whether these two properties are free space properties or not. So I have to put just question marks here. And well, at least these ideas are useful to show that for Weierstrass countable tightness, we do get free space properties. So for the moment, this is a draw. We have two free space properties, two properties which are not free space properties, two properties that we do not know. And well, concerning having Weierstrass, okay, let me insist a little bit more about these two questions here. So, as I said, I don't know whether having Weierstrass sequential dual ball is a free space property. I don't know whether property prime is a free space property. I really think that the answer is going to be affirmative. Maybe it's not so difficult to adapt the proof. And well, if one wants to give a positive answer, it is enough to answer in the affirmative these two questions here. So I wonder whether having Weierstrass, the twisted sum of Banach spaces with Weierstrass sequential dual ball do have Weierstrass sequentially compact dual ball, and the same for the convex version. So this is, if we try to isolate this from the topological point of view, a related question would be the following. So suppose that we have a sequentially compact space K, and we take a countable discrete extension of K, which we call M. So this is something which appeared yesterday in the talk of Alberto. So this is just a compactification of the natural numbers of omega in such a way that the remainder is homomorphic to K. So under what conditions can we ensure that for a compact space K, any countable discrete extension is also sequentially compact? So this is the question, and in particular, I'm interested in the case in which K is sequential. If K is sequential, is it possible to construct a countable discrete extension which is not sequentially compact, or on the other, or in the opposite? Or every countable discrete extension is sequentially compact. And well, this is more or less related to a recent result of José Rodríguez and I, where we proved that, well, we showed that in general, if K is Evelyn, Corson, Raman-Coding, this is fermented by a metric, or its weight is small in the sense that it is smaller or equal than the splitting number. In all these cases, any countable discrete extension is sequentially compact. Okay? So the problem is that all these cases are not covered in the case of sequential spaces. And well, our motivation for this result was not this one, but a question of Manuel González and Tomek Kania. So as an application of this result, we proved that we have a Banach space which is Grothendieck and a subspace which have a quotient which is reflexive, then this subspace Y is Grothendieck. So these kind of questions also have some applications outside the setting of just sequential compactness. So also inside Grothendieck's property. So Grothendieck's property, which was defined, was also appeared in the talk of Gilles, means that every weak star null sequence is weak null. So here the Grothendieck's property does not pass to subspaces, and Manuel González and Antonio Cania were they posed several questions concerning, well, if Y is big enough, then can we ensure that Y is also has Grothendieck property? So in particular, they asked if this holds whenever this quotient is reflexive or whenever the density character of the quotient is smaller than the splitting number. And well, in all these cases, the subspace is Grothendieck, and just essentially because of this fact here, because total discrete extensions of, let's say, good compact spaces are sequentially compact. Okay, so I have to add here a small question mark. And well, this is a side question mark because I haven't gone too deep in the literature, but as far as I know, I think this is unknown. So if any of you know something about whether this is a free space or property, please let me know. I think this is unknown. And well, the last property that we have to consider is property of Efremov. Notice that the non-convex version of this property is weakest Calendarlic dual, which is not a free space property. So one may expect that this might also provide a counterexample to this property here. So maybe Johnson in the source space failed to be to have property E, and therefore this property E is not a free space property. So this was already asked in 1980 by Flitzko and Jost. So they asked whether Johnson in the source space has property E. They also asked whether property C of Thorson imply a property of Efremov. Concerning this last question, Jassi Moore and Christina Breck, they independently provided consistent examples of Banach spaces which have property C but not have a property of Efremov. Indeed, these examples do not have property E prime, so the dual body is not sequential. And well, Jassi Moore's example is done under diamond, and Christina Breck's example is done under some particular forcing. And well, the question still remains instead of C. So indeed, one may think that in general Johnson in the subspace does not have a property E of Efremov. And well, some years ago, Antonio Avilés, José Rodríguez and I, we proved that under the continuum hypothesis, there are mad families for which the Johnson in the subspace and the CK space of the corresponding mad family does not have property E of Efremov. And we also proved that there are also other families for which the corresponding space do have property of Efremov. So it depends on the family. Okay. Well, so it remains this question: what can be done without using the continuum hypothesis? So Alberto and Plebanec, they succeeded constructing this almost disjoint family for solving the complementary space problem without using the continuum hypothesis. Niels and Schmieder also constructed an interesting almost disjoint family without using the continuum hypothesis. So it looks like we are the only ones who need the continuum hypothesis to reach our goals. So for those who know how to construct interesting families without using continuum hypothesis, I invite you to think of this problem, because we weren't able. And well, let me go back again to the diagram. What we have said is that this implication here does not hold, at least under continuum hypothesis. This implication here does not hold, at least under continuum hypothesis. And well, this implication here does not hold, at least under diamond or under Christina Breck's forcing. And concerning this last implication, I have nothing to say. I really don't know in ZFC or in any consistent result containing this. Well, yeah, I'm going to say one thing at the beginning of the talk. At least one consistent result. So let's go again to this question here. As I said, whether this implication holds is false question. Well, related result to this question is a result of Frankiewicz, Banach, and Wilner-Zewski, who proved that if we only deal with CK spaces, then under Martin's axiom and the negation of the continuum hypothesis, every CK space with property C has dual ball with Weierstrass countable terms. So the implication holds for at least for CK spaces. In a work in progress, Alejandro Poveda and I, we proved that under the proper forcing axiom, this can be extended even to Banach spaces, not only CK spaces. And notice that proper forcing action is something much more restrictive than the Martin's action and the negation of the continuum hypothesis. In particular, PFA implies Martin's action and the negation of the continuum hypothesis. But well, at least we can close this implication here. And in general, what happens under PFA? We were interested indeed, notice that the diagram was this one, indeed, what our initial goal was to try to adapt this implication, which holds under PFA, to this implication here. So we were wondering whether under PFA this implication holds. But we realized that under PFA, even this implication holds. So if this holds, this holds, this holds, and this holds, what we will have is that these four properties are all equivalent. So under PFA, the diagram is much more simpler. So we do have four properties which are equivalent. So these 8 properties indeed are at most 5 different properties. And the only remaining questions under PFA would be that whether this implication holds or whether this implication holds. And well, if we go back again to the table of free space property, what happens under the proper forcing axiom? Well, we do know that property C of Corson is a free space property, and under PFA, property E prime is equivalent to property C. Having Weierstrass sequential dual ball is equivalent to property C. So in that case, we have here that this is a three-space property. We do have here that this is a three-space property. And the only remaining questions are these 2. As I said before, I really think that these are three-space properties even in ZFC, but this is unknown. So just want to let you know that at least under PFA, we do know that they are three-space properties. So don't look for a counterexample at least in ZFC. And well, this is all I wanted to say. This is the main references of this talk. And well, this is the last work that I mentioned. This just a work in progress, which is still not in IQ. So thank you very much.
So you mentioned that you could control the sequential. Oh, thank you. So you mentioned that you were able to control the sequential order of a twisted sum of 2 spaces. I was thinking about a possible converse, at least in some subclasses like CK, or maybe a little bit more general. If you have a Banach space of some sequential order, let me say 5 or maybe something infinite, could it be that it would be a subspace of a twisted sum of 4 or 5 spaces of sequential order 1 or something like this, you know? I'm trying to find like insolvable groups. That is, you would have towers of spaces with small sequential order that would generate everything, at least again, if you have some structure around, you know, it's exactly as if you're... Yes. And maybe for CK it could be easier than in full generality, but did you try in this direction?
Yeah, but well, you can do this in the CK space because you are dealing just with scattered compact spaces. So more or less you have like an ordered structure, you have levels, so you have
Yes.
something to work with. But in general, well, this, I mean, it's not so clear that you can define levels where you have, let's say, like the biggest subspace having sequential order 1. So you can, I mean, you can translate the question just to the compact setting and topological setting. So any sequential compact space can be decomposed as a more or less a dense increasing sequence of sets having sequential order 1, then having sequential order 2. So we are adding levels like in the scattered compact case. And I really think this is unknown. But as I said before, essentially the only sequential compact space which is known is this one. There are no more.
For instance, one, I mean, it's an ambitious question, of course, but one class where you could try would be the non-commutative version, that is C-star algebras. You know, you have a notion of scattered C-star algebras, and there, of course, it will be more difficult, but there is maybe some hope of a structural result like this. Okay. You don't have to answer this on the spot, okay? It's just a direction of research, I mean, behind this.
Good. Thank you for coming. My plan is not to present any theorem, any result, anything. We will just start some diagrams for, say, half an hour and go to lunch, right? So, yeah. Almost ready, almost published. I brought with me some flyers. You want to pick at them. And we'll soon be ready with everything we knew about exact sequences and homological stuff. And these are the authors. That picture is from the first day we started with the book, and this from the last day we ended with the book. You can guess who are the authors. So, diagrams. These are diagrams. Anything you can pick with points and arrows. You want to think of Banach spaces, points are Banach spaces, arrows are linear continuous operators. That could be any other thing. In the first case, 3 points, 2 operators. I don't pick to the identities. It is assumed that there exist identities, right? One point to itself, like in the second diagram. 2 points, 2 spaces, and identities, nothing else. And the first infinite diagram one can picture, sequence of arrows. Sometimes these are called small categories, categories that you can paint, you can draw. And the best thing you can do with a diagram is to make the limit. The limit of a diagram is another object, in our case, a Banach space, with the property that there are arrows from the points in the diagram to this limit, say. If this is your diagram, the limit is an space, in our case, another object, together with arrows from all the points into the space, right? At least if this is direct limit, if this inverse limit is on the opposite side. Arrows flowing from the space to the space. Making all this commutative and with a universal property. I mean, any other space you can put with arrows making everything commutative, there exists a unique arrow from the limit to it making everything commutative. One example. I did it on purpose. I draw the direct and I put an inverse limit. The inverse limit of this diagram, two spaces, just identities, is the product. It's another space here, two arrows, projections, and with the property that any other space you put with projections factorizes to the product. That's the definition of the product, the limit of that diagram. Or another example, the direct limit, now arrows go to, is the inductive limit. One space, arrows from the spaces into the limit, and with the property that for every other space you give me with arrows, there exists a unique arrow making everything commutative. The theorem here, I think from Semadeni and Sinenberg, is that in the category of Banach spaces with contractive operators, I mean operators with none less or smaller than one, there exist limits. Anything you can take, you can make the limit. There exists that construction. Such as the product of a finite number of spaces, such as the limit, or favorite, the direct limit of that diagram is what we have been calling these days push-out. A space you can put there, two arrows making everything in the square commutative, and for every other space you can imagine here, with two arrows making this commutative, there exists a unique arrow making the whole diagram commutative. And this is one of the tools we must use when working with diagrams. Then we have exact sequences. You can see I don't bother with the names of the spaces, the dots. An exact sequence is a diagram like this, but with the property that the kernel of each arrow is equal to the image of the previous arrow. At least in Banach spaces is that. Categorically speaking, it's a bit different, but well. Oops. And the nice thing is what happens when you mix both exact sequences and diagrams and limits. Because if you have an exact sequence, one operator here, then automatically you can make the limit of this diagram, the push out, and because of the properties of the limit, because the limit is not one space making the diagram commutative, it's one specific space making the diagram commutative and with some universal property. For that reason, this push out here produces this another exact sequence and this whole diagram. And the same we do the inverse limit, which is called the pullback. The connection with classical problems in Banach space theory is that, let me see if I can do this. An exact sequence like this in the Banach space world means a Banach space here, one subspace and the quotient space. Every exact sequence you draw, in the end, is that. And the point is that this exact sequence is called to split. And to split means that there are arrows the other way. This means that the subspace is complemented. This is not the best way to say things in the diagrammatic world, but the subspace is complemented. And the connection here is that this sequence splits if and only if this operator can be extended. And this sequence splits if and only if this operator can be lifted. So we have a connection between complemented subspaces, diagrams, and extension or lifting of operators. And this is the combination that works. This for us works sometimes. So, we are ready. we will look at a couple of more diagrams, and that's nothing serious. For instance, this one. Where did I get this one? Well, I get this one taking an exact sequence, one operator, but this operator, let's assume this is a quotient operator. So if this is a quotient, you have the exact sequence, it defines the kernel and so on. Now here we put the push out, and you mix all together, and you get this diagram, which conceals a lot of information that we need sometimes to uncover. For instance, this that is, as I said, a push out diagram, clearly, right? Arrow, arrow, push out. If you turn, I tried to do this slowly, but I couldn't. So if you turn, now it is a pullback diagram. It's a pullback, right? Arrow, arrow, pullback space, things at one. Moreover, let me say a couple of things that cannot be seen when you look at the diagram, but with some care you can. Whenever you have this diagram, in this form or in the other form, there is another exact sequence here that begins in the space, passes to the product of these spaces, and ends here. It's called the diagonal here. This is because of the very definition of pushback, of pullback, or push out. The very definition is hidden here. In the same way that you can also prove that this behaves in a quite symmetrical form. For instance, if the sequence above, this middle sequence, can be obtained as push out of the lower sequence, then the same happens to the other two. Then this sequence, this can be obtained as pullback of the lower sequence. All these things are mixed here, there. We gave it names, diagonal principles, parallel principles, but the point is they are tools to do things with the diagram from the very moment that you have a couple of arrows and one operator. Then you make the push out or the pullback, they are the same. Then we have the diagonal, we can do, all this is mixed in this simple diagram. This is the same painting, but a bit different, right? Instead of starting with a quotient, I start with an embedding. So look at it for a moment. This is a pullback diagram. It's also a push-out diagram, but not in the same way. And let me give a using of this, just to say something. After all, this is a congress on CK spaces, right? So let me say something. Yeah. Probably the first theorem which some name I could prove is that the Danforth-Pettis property is not a three-space property. We don't care what is the Danforth-Pettis property now. But you can do this. Pick any Banach space, any separable Banach space to make things easy, and put this space into the continuous functions of zero. You can do that. Make the whole sequence. Right. Put 0, 1 as a quotient of little 1. And complete the diagram like this. So you get something here, pull back, see the kernel, whatever. This diagram in this particular situation. So as I told you, here and here, you have the diagonal sequence that begins here. In the middle is L1 plus X. This is the quotient, and this is this sequence. Look at it. Without knowing which is the Danforth-Pettis property, of anything, we know that CK spaces have it, like this one. We have that L1 has the property, as well as any of its subspaces, like this one. So this has the Danforth-Petit property, this has the Danforth-Petit property, and the Danforth-Petit property passes to complement its subspaces. So if X does not have, this space cannot have. So here you have a counterexample to the free-space problem for that property. That works for any property that some spaces have, that complementary subspaces have, then you can draw something this way. So in this very simple way, you can obtain some results of interest. Oh yeah. You remember yesterday in the thesis a moment that there was a kind of discussion about how Alberto did from an argument to passing from a push out to a pull back and so with CK spaces. Let's make it. If I remember the name, this is the compact made with the family A, this is the compact made with the family B. So you put C0 inside, the quotients are equal, and somehow via the result of Plebanek and Marciszewski, we know that this pullback sequence splits, right? Because every sum of this and zero is zero. So the pullback sequence splits. This means that operator on the right, the quotient can be lifted like this. So you lift it. And this operator lifted, which is restricted to the kernel, must go to the kernel. And now, I hope I would like to do this slowly, but I can't. You have this diagram, right? Put it in parallel. Look at this. And this, no matter if it looks different, is a push-out diagram. Not pull-back, it's push-out. Make it the other way back. And this is the way in which you can pass from a pull-back result to a push-out result. All these are mixed one with the other. And the same the other way. So, one more diagram that one finds here and there is this one. Two exact sequence, three operators making this commutative. Not very long distance from what I've been talking up to now, because this diagram you can split this way. This is the first operator, this is the second operator, that is the third operator. But here above you have a push-out diagram, and here below you have a pull-back diagram. Yeah, you need to check that it's on the other way, not back. So this splitting of this diagram into pullback and push out allows you again to use the same type of techniques of lifting, limiting, extension to try to say something. Not as much as the thing we would want. And these type of diagrams can be serious sometimes. So let me go back to the Carlton-Peck space, set 2. It's a twisted sum of Hilbert spaces, and for who is not familiar, this is not the moment to get into, but the point is the problem of knowing which operators that exist in the Carlton-Peck space is a serious problem. There is something difficult, something hard, and something very interesting inside. So let's try to face this. Which are operators? Among the other operators, there are a particular type of operators, those that make this diagram commutative. It's not the same, because these are operators that, when they're restricted to L2, send it to L2. A general operator does whatever he wants. The difference between the diagram above and below. Well, the above is a diagram we cannot study, we don't know what to do, and below we can do a lot of things. Operators, just from set 2 into set 2, have this general form. These are 4 operators defined from L2 into somewhere, into some place, linear, probably unbounded, probably do whatever they, but when they mix, they get an operator on set 2. But this could be just linear operators. not continuous. So that's difficult to handle. But when the operator has this form, it makes a commutative diagram, then has this beautiful. It's an upper triangular matrix. An operator with an upper triangular matrix are nice. For you. For instance, the problem that Gilles mentioned, that hyperplanes of theta 2 is controlling to know if the hyperplanes of theta 2 are isomorphic to theta 2. This nobody knows. But in this language, is if every operator on theta 2 is a strictly singular perturbation of an upper triangular operator. How could one do that? Well, that's not as easy, and probably here the original representation, maybe this is not too much. I mean, you can try to decompose this into a triangular operator and leave the other one, but I told you that this delta, alpha, beta, gamma are just linear maps. Go wherever they want. So, on the other hand, operators, upper triangular operators can be connected with other type of problems, such that operators that come from a scale of interpolation. In the case of set 2, the scale of empty spaces. For instance, you have this operator on the left, on the right, some operator acting on the scale of empty spaces. And with this I mean that it sends L infinity to L infinity, L1 to L1, so automatically it sends L2 to L2. Then that matrix works as an operator in set 2. If this is not an operator in the scale, but can be inserted into the action of a group on the scale of LP spaces, then still you can obtain a triangular operator. This is the operators in the scale, but this is the derivative with respect to the parameter of this operator. So still you get a triangular one. And the best example of that type of thing is are the beautiful operators that Carlton introduced in several papers. He obtained many results with them. We have that form. That's the Carlton-Peck map. Right? If you pick this type of operators, upper triangular, then you can generalize them to still see that they are upper triangular operators. This is the general version of the space set 2, or the general version of the Hilbert space, which are the Rochberg spaces. L2 is the first Rochberg, set 2 is the second Rochberg, the scale for the scale of spaces, and these operators work as linear continuous operators on them. Moreover, with these operators, in the same way that Carlton and Swanson proved that set 2 is a symplectic Banach space with a non-trivial symplectic structure, you can prove that all these spaces are symplectic with a non-trivial structure. It's not exactly straight the way, but it can be done, right? And I think this is all. Thank you very much. Questions? Remarks?
Since you mentioned C2, thank you. Thank you. Since you mentioned Carlton-Peck space, I believe it's still open, and I wanted to ask you about this, whether a non-trivial twisted sum of Hilbert spaces always fail a local and conditional structure. I mean, Nigel showed that it cannot have an unconditional basis if it's non-trivial, but I believe that for local and conditional structure, he did not know. Do you know if there was any progress in this stuff?
When we prove, the difficult thing is to prove that the twisted sum has not local and conditional structure. One can prove that these Rochberg spaces do not have local and conditional. Having the actually described CR example has not local and conditional structure. It is an L2 sum of finite dimensional space.
No. Maybe I did not express myself properly. If you have a twisted sum, which is really twisted, of L2 spaces, let me formulate it differently. If you have a twisted sum which has a local and conditional structure, then it would be trivial necessarily. So, I believe this is where the ball.
Closest thing is Carlton's theorem that it has an unconditional basis must be.
That's right, but I believe that in the same paper he asked the question whether local and conditional structure was sufficient, and I was wondering whether there was anything new in this direction.
Anyone else? Okay, thank you very much. Thank you.